So, till now we have studied some of the MAC protocols. Those were basically the contention based protocols and the contention free protocols. In the contention based protocols, the protocols that we studied were the aloha, the pure aloha you mean, and the slotted aloha, and you have the CSMA, right, CSMA and CSMA CD. Coming to the contention free protocols, the protocols that we studied are the bitmap and the binary countdown protocols. So, we have one more kind of protocol that is to be covered in this MAC layer, the token based protocols. But before the token based protocols, we will study some of the standards that are being used for the MAC protocols, or what we say the IEEE 802 standards. You know, this is a very common 802.x is a very common forum or a standard. Till now you are using for all this Bluetooth, your personal area network, wireless communication, Wi-Fi, WiMAX, everything. So, this starts with the 802.1, which basically describes the basics of your standards. So, we do not go for the details of this 802.1, basics of the all the 802 standards, and 802.2 that basically focuses on the interfaces required for this protocols and all. So, next to this, coming with the 802.3 is a very popular standard, and the origin of this standard came when, as we discussed, the aloha protocol, the beginning of your MAC protocol. The people of the people of defense people in the Hawaiian island, what they started to communicate with a they stationed 100 workstations over a span of 1 kilometer, and they connected all these stations or workstations through a cable and started communicating with each other. So, because the communication starts with the cable, or what we say is an ether. So, the 802.3 standard says the Ethernet standard. Ethernet meaning the network with the cables. Usually when it is asked what is Ethernet, people say it is a card, it is a connector, it is a something. So, Ethernet is nothing but it is a standard that specifies the network made of the cables. So, what this 802.3 specifies? This usually specifies the different kinds of cables required for your wired network or wired connection. So, very popular kind of ethers or the cables required for the data communication are the 10 base 5, 10 base 2, 10 base T, and the final is a fiber optics. So, the recent invention that what we have seen is the fiber optics, or this is also named as 10 base F. So, till now people are working on the fiber optics, and it is vastly used because of its speed, the capacity, as we discussed in the last class. Why this is used? Because it has a high capacity to transmit the data. So, coming to the 10 base 5, this cable is also known as the thick coaxial cable. Usually this is yellow in color. So, if you have a cable like this, the core of the cable is here, that really transmits the signal, you can say, surrounded with a thick coaxial cable, and with every span of 2.5 meters, there is a mark or demarcation on the cable. This demarcation indicates where the tapping has to be done. Why you need the tapping? Usually the transceivers are tapped into this cable, and they go halfway to the core of the cable for this connection. And what is the job of these transceivers? Along with the transmitting and receiving of the signal, this also does the collision detection and the carrier sensing as well. So, all that CSMA CD protocol that we studied in the MAC protocol, that comes under this 802.3 standard, the Ethernet standard. So, Ethernet starts with CSMA CD. The basic starting or the basic designing of this protocol is with the thick coaxial cable, and where you have that, let us say this is a transceiver, it is completely tapped onto the cable, and it is halfway it is gone to the core, how they do this CSMA-CD or how they do the collision detection. Usually at the end of the cable there is a electronics attached to this called, can anybody say, a terminator. Usually a terminator is used in any cable. The reason for using the terminator is to keep the signals intact inside the cable, right. Now what happens, let us say this transceiver is connected to a node here, and now the node wants to sense the carrier or to detect the collision. So what it does, it sends a signal, a pulse to the carrier, I mean to this core of the cable, and when the signal passes, there is a mechanism associated with this. Either the signal will come to the end of the cable, then it will reflected back as an echo, or if in between somewhere there is another signal or anything happen to be present, it may again echo back to the signal, I mean to the sender. Now this sender has the transceiver has the mechanism to analyze the time of getting the echo, so that it can understand whether the echo has come from the terminator side or the echo has come from somewhere else in between the cable, and this mechanism is called the time domain reflectometry. So with this mechanism the transceiver can say whether there exists a carrier or signal in the channel or not, or if there happens to be any collision or not. This will say, or this will, in this way the node sends the carrier to understand if there is a collision or not. If there is any collision, immediately the transceiver sends the message to the node saying stop transmitting to the channel, because there is some other signal in this. If the echo comes from the terminator, meaning the total channel is free, so it can send the data into the channel now. That is what is the job of the transceiver. So for that reason you can say the nodes can be connected with every 2.5 meters distance to the thick coaxial cable, right. And the third is the 10 in the name specifies the bandwidth of the thick coaxial cable is 10 Mbps. The bandwidth is 10 Mbps with which it can transmit the data, and the term base says it supports the baseband signaling. Some of you must be knowing what is a baseband signaling. So baseband signal is being supported by this thick coaxial cable or 10 base 5 cable, and the 5 says the length of the cable could be maximum 500 meters. So usually your workstations or high end systems, they are connected to this thick coaxial cable, and this coaxial cable is put at the back end with the transceivers attached at every 2.5 meters distance, and you can attach your workstations or servers to those transceivers, and you can imagine how many transceivers or servers can be connected to a 10 base 5 cable as its backbone. That is what is the first basic kind of LAN that was started with the collision detection mechanism and all. The next one was the 10 base 5, sorry, the 10 base 2. The name says 10 base 2 is your thin Ethernet, thin coaxial cable. This is thin coaxial cable with same principle, but the cable is very thin and it is flexible. It is cheaper, it is flexible, easy to trench and all those things. Usually the color of this one is grey or black. Now instead of transceivers, because transceivers are the costly equipments, instead of the transceivers, when the nodes are to be connected with this 10 base 2 or the thin coaxial cable, what they do, the cable lies here with again 2 terminators at the end. This is the 10 base 2 cable, and this cable is connected to the node with a connector, special connector here called the T connector, or usually it is a BNC connector. That means if this is a T type of connector, this goes to the cable and one end of this one is connected to the host 1 and the other one is connected to the host 2. This is how the BNC connector or T connector is. That means a small tapping is done at the cable, and this tapping connects two ends. One is this end to this host and another to this host, this one. Again the same, here the T connector. This is how the connection is usually done. And this T connector or the BNC connector again does the same CSMA CD does, what the thick coaxial cable does, but with a less precision. So, when the LAN is set up, when a set of nodes are connected through this thin coaxial cable, usually your normal nodes, what we are with the normal computer or PCs, they are usually connected with this 10/2. When the servers are connected to the 10/5, your normal workstation, I mean normal computer PCs are connected to the 10/2. Here also, as the 10 says, it is again the bandwidth is 10 Mbps, again the baseband signaling, and 2 says the length of the cable is 200 meters, and within this 200 meters maximum 30 nodes can be connected. So, if you have a small lab which can accommodate a 200 meters length of cable, thin coaxial cable, and you can work with 30 nodes maximum, you can go for this option. So, both of these 10/2 and 10/5, what they have? A bus structure actually, either a 500 meter length or a 200 meter length, and the nodes are tapped into the cable. Now, let us say there occurs a damage or break in the cable in between. So, how to detect the damage or a cable break for this both the kind of thin and the thick coaxial cable? In that case, your whole of the network has to be down or that gets affected. The reason is that you do not know in which area the break has the damage has occurred. So, the testing of the cable is very difficult when you have any of these two kinds of connection. If only one node is, at one point the system is either the cable is damaged, whole of the bus is or whole of the cable is damaged, affected. All the nodes, 30 nodes or any number of nodes, they are affected by this. That was the drawback of your thin coaxial or the thick coaxial, for which those two were replaced with the another kind of cable called the 10/T, where T stands for the, can anybody say this? T stands for twisted pair. It is a twisted pair. Have you seen the cable of the telephone cable, telephone wire? This has the same structure as your telephone cable. 4 to 5 pairs of thin cables are twisted to form another set of cable, and what you do, you connect to the end of the cable, both end of the cables are connected with a special kind of connector called the RJ45 connectors. You tap the RJ45 connectors into the both side of the cable and plug this RJ45 to your hub. So, the structure of this 10/T or the twisted pair kind of cable is, if you have a complete set electronic set hub here, this hub is connected to any number of nodes depending on the number of ports supported by the hubs, 8 port hub, 16 port hub, 32 port hub. Depending on the size of the hub or capability of the hub, you can connect any number of ports into it. That is what is your 10/T cable. And the maximum length of any cable from the hub to the node is 100 meters, or max you can go for 150 meters. Usually it is 100 meters, because then after the attenuation is so high, your signal is slow down or you do not get the data properly. So, that is the drawback of this, but the strength of this kind of structure is that if a single cable is damaged or it is not working, only the node connected to that cable gets affected and rest all are remain unaffected, they can work. That is the biggest strength of this 10/T cable, for which this completely replaced all your thin coaxial, thick coaxial cables. And now whatever you are using to even your PCs, what you are using? If you have a LAN, other than Wi-Fi you have a LAN, right? What do you have? The same 10/T connection. You connect to the port, then you connect to your Ethernet port and you do the same thing. So, this is a very popular your cable, and this also supports the 10 Mbps with baseband signaling. 10 Mbps with baseband signaling, that is 10 base T or twisted pair cable for the communication. Now, this, as you know, the flaw of this kind of cable is 100 meters. If you want to have a larger or big network or a lab setup, you cannot think for a this 10 base T cable. The reason is that after 100 meters, it starts attenuating the signal and the signal loss is very, very high. And it also the when you are connecting high end servers or high end computers to this, it is difficult to work with this 10 base T. It is only good for the nodes connected to the hub. Now, if you think of a strong backbone supporting the high speed data communication, any of this, maybe thick coaxial cable was a good option, but again you know the maintenance of the cable was too expensive and costly. So, then people thought of the most important or the very popular 10 base F, and usually we think of this one for the backbone of your network. We do not use a fiber optics for connecting our node to a port, it is not possible, we cannot afford even. So, what you do, usually your backbone of your network remains as 10 base F, and this is connected to the small hubs, you can say, at any building or lab or anywhere, the different hubs. Hub is again replaced with the switches or the managed switches, unmanaged switches, all those things are there. So, we are just simply considering a hub having a multi-port. So, now from the port onwards, you can have your all the nodes or small pieces connected to the hubs. So, at the backbone you have a high end communication channel with large capacity, and then your pieces are connected to the small hubs and hubs are connected to the fiber optics at the backbone. That is what is the current trend of your networking if you are thinking of a wired network. Forget about the Wi-Fi, the wireless structure, we are not considering that right now. Now, again let us say fiber optics, again it has a limitation. Any cable has got a limitation, it can work up to a certain distance, and then after it has to be connected with a special device so that it can again strengthen the signal, because as you know when the signal passes at one point, the strength reduces due to the communication channel attenuation, noise, all those damages and all, it goes on, the strength of the signal goes on decreasing, and at certain point beyond that if you cannot this this low magnitude of the signal is not accepted for your communication. So, what we do, this is what you say is a threshold point. So, at this threshold point you have to amplify the signal again, amplify the signal and again retransmit it, or you can say forward it again. So, who does this? At this point when the signal level goes beyond the threshold value, a special electronics device called the repeater. Usually the repeaters are used, you will see in many of the network this wired connection, in between you have the different repeaters, and these repeaters what they do, they amplify the signal strength again and forward it to the next some distance. That is how your Ethernet works, or the network with different cables that work. While starting with the thick coaxial, thin coaxial, then you have the 10 base T or the twisted pair and the fiber optics. You can have the combination of any of this depending on the scenario or depending on the requirement of your network or your LAN setup, and that can be done. With this, with all these different kind of Ethernet standards and all, we have a frame format. We have a frame format, common frame format like DLL. If you remember, SDLC was a common format, a basic standard for the DLL protocols. So, you have also a 802.3 MAC layer frame format. This frame format for 802. What this says, if I consider this in terms of byte, the first field is a 7 byte, the second is a 1 byte field, then third is a 2 to 6 bytes field, again this is again 2 to 6 bytes, then this is a 2 byte field, then you have a variable byte field, then you have another field which remains from 0 to 46 bytes, and finally you have 4 bytes length. This field is called a preamble field. The first field of the frame format is a preamble field which is of 7 byte length, and all these 7 bytes are of this form. Every byte is of this form, 1010 form. Why you need a preamble signal? Synchronization. You need a preamble signal to make the receiver and transmitter in sync with each other. So, this is required for your synchronization of the receiver and the transmitter. For that reason, you have a preamble signal, and followed by this preamble signal, you have another 1 byte signal called the start of the delimiter field, SD, start of the delimiter field. This is a 1 byte field of the same pattern as the preamble, 101010 followed by 1 and another 1. This 1 indicates end of the boundary of all these preambles and the start delimiter and the end delimiter field. So, you have this field of 1 byte, at the end you have a single 1 indicating the starting of the actual frame. Then next to that you have the destination address field, means the receiver. Who is the receiver of this frame? As you know, the different kind of communication modes are there. The receiver could be one receiver, it is unicast. It could be group of receivers, it could be multicast, or it could be all the receivers, it could be broadcast. So, that will be decided by this addressing of 2 to 6 bytes. It could be anything depending on the size of the network. 2 to the power 6 bytes means if 2 bytes are used as the number of receivers means 16 bits. So, how many receivers can be connected, or how many nodes can be connected to this LAN, right. So, now you can imagine how scalable this protocol can support. Depending on that, you can have a unicast or multicast or a broadcast receiver or a signal. What it says, the MSB, the high order bit, most significant bit of this address says if it is a 0, that means this 0 followed by some address will say it is a unicast message, means the person or the node having the specific address will receive the frame. If it starts with a 1 followed by some specific addresses, then it says it is a multicast, and this indicates the group and the nodes belonging to that group will receive this frame. Now, if the destination address is all ones, this says this is a broadcast message. So, your destination address field itself will specify what kind of communication is being supported by this frame. So, your bit structure of the address will specify that. Next to that is your source address. Source address means the node who is sending this frame, who is generating the frame for the receiver. So, having any of this 2 to the power 16 to 2 to the power 48 number of addressing scheme, the address of the source could be anything, right. Then the next field is, this field is the length of the data field. This is the length of the data field. Usually 2 bytes means how many bytes of data are there. If this is 2 bytes, that means 2 to the power 16 bytes. The length of the data could be 2 to the power 16 bytes size. Okay. That way it decides how many, the next is the data field, I will come to that. What is the total amount of data bytes are there, and what is the length of those bytes will be decided by this length of the data field. Then you have a variable field, the actual data, and this data can vary from 0 to 1500 byte size. And to indicate this any of the byte size, how many bytes are there, that will be decided by this length of the byte field. Depending on the amount of data that is being generated by a node, your data field will be 0 to 1500 bytes. Then next you have a special field called a padding field. We will come to know about why this padding is required later on. But next to that you have the error detecting field called the checksum field. This is again 4 byte. Usually checksums are 4 byte fields, right. Now with all these contents a frame is generated, perfect. Now whether the frame is a valid frame or it is an invalid frame, how the receiver decides. Forget about the checksum. Checksum will say there is an occurrence of error or not depending on the number of bytes present in the frame. But before checking the error, it must be indicated whether this frame that is being transmitted or received is a valid frame or not. To know that, the protocol says that the length of the frame must be at least 64 bytes. 64 bytes from the destination field, destination address field till the checksum, Now let us assume that there is a frame which does not carry any data. It may happen, there are certain frames that may not also carry some data, some control information they are carrying. So in that case, what will happen to the, what will be the data field then? 0 bytes of data are there, no data is there. So what is the length of the frame then, starting from destination address? Let us assume even that the maximum frame size, the address size is 6. So your address field is 6 byte plus the source address is 6 byte plus the length of the data field is 2 byte plus the checksum is 4 byte. So total is how much? 18 bytes, which is less than your 64 or the required data. Can we say this is an invalid data, invalid frame now? No, because though it does not carry any data, but still it carries some control information and we cannot say this as an invalid frame. So in that case, what the padding field does, it fills up the rest of the data starting from 0 to 46 bytes. So if no data is there, this plus this 18 plus 46 is equal to 64 now. So now your frame becomes a valid frame. So when the less number of data are being carried in a frame, to make it still valid, your padding field fills up the rest of the field saying that this is a valid frame and the contents of the frame has to be executed by the receiver and so on. That is what is the principle of your MAC layer and a basic MAC layer, MAC protocol, any MAC protocol, and then they can have different structures over that and they can work on how the tokens are being transmitted, how the control messages are being transmitted, that we will see in the later part of the story, right. This is what is the basic frame format for 802.3 or the CSMA-CD protocol or all these cables that we are studying. Okay. Next in the next class.